Good morning. We're going to be going over the vertical oscillator right now. So let's get started. So we have this spring that's attached to a block, and eventually somebody gets it oscillating, and it's something that's going up and down. It's just like the lab that we were doing before all this craziness happened. So let's read through this. The diagram to the right shows a block attached to there's that word again, Hookean spring. We talked about this in the last video. That just means that the force of the spring, or whatever is going on, follows Hooke's law. That pen's being super weird right now. Okay, so follows Hooke's law. And all right, the block hangs at rest at position B. So this part, remember, that's what we call the equilibrium position. And the equilibrium position is special because it always tells us that that's where the net force is 0. All right. The block is raised to A and released. The lowest position is when it reaches part C down here. So when it's raised to block A, it looks like this over here on the right that I kind of sketched out. And then when it's at C, it's stretched all the way down to here. Okay. The block then oscillates between A and C. Consider point B to be 0 position. And then anything above B is positive. So if this is 0, anything up here is positive, and anything going down here is negative. All right. So first part, sketch a force diagram for each of the positions. So if I'm sketching a force diagram here for each of these, okay, it's the same block that's attached to the spring the whole time. So right away I know the force of gravity on each one is going to be the exact same because the object's not changing. So the force of gravity, we want to draw those vectors to look like they're the exact same length, and then label force of gravity. And then the last thing we can do to show that they are the same length, in case so we can take like any confusion out of it, is put tick marks. All right. So all of those are now the same force of gravity, and the only thing that's going to change is this spring force that's pulling up on the block. And one thing it says in our instructions, during the oscillations, the spring is only being stretched, never compressed. So if you think about that, if it's only ever being stretched, when something goes from being stretched out to compressed, the direction of the force of the spring changes, right? So if it's only ever being stretched, basically what that's saying is that the spring force is only ever going to be going the same direction. So for us, it's going up. So it's always going to be going up. So at part A, that'd be like right here, right? We got that force of gravity going down. We know that this block needs to accelerate down, right? It's stretched out a little bit. Well, if it's stretched, there's only going to be a tiny spring force, because we know that the net force for this, it needs to go back down, so the net force should be in the downward direction, right? And the only way I can do that, the force of gravity can't change, so the spring force here needs to be smaller than the force of gravity, okay? Now at position B, remember it said this is where it wants to just hang at rest. This is the equilibrium position that we called it. So what the equilibrium position tells me is that all of the forces are canceling each other out. The net force is 0. So I know that that spring force, when it's at that position, is going to be the exact same magnitude of the force of gravity. Right? When we are at position C, if I can get down to it, there we go. Remember, this is still the force of gravity right here. However, this spring, think about Hooke's law, right? Hooke's law says that if this x gets bigger, the amount it's stretched gets bigger, the spring force gets bigger. So if it's been stretched out more, the string force is going to be greater. So at position C, the spring force needs to be bigger than the force of gravity, and we can write that right there. So to kind of give us an idea of each of these positions, at A, the net force is going down. At B, the net force is 0. And at C, the net force is going up. And then it's going to be the same anytime it reaches those positions. Okay, so again at B, crying baby in the other room. I might have to pause here in a second. The spring force looks like that. And then at A, the spring force is back to being real tiny. So we got our force diagrams drawn. Okay, and then so the next part says sketch the graph of the net force acting on the block as it goes through each of these positions. So it really helps that we kind of already talked about what the net force is. So it starts at position A. So at position A, the net force is negative, right? So since we're starting here, you can look at the labels. We're starting at position A. I know it's going to start with a negative force. So I draw a dot. At position B, that's the equilibrium position, and the net force is 0, so I know that the net force is 0. At C, we have a large positive net force. So I got a big dot up in a positive direction. Okay, and then we just follow through that same pattern. It's very, very similar to the last worksheet we did. And then we can fill in our dots with, remember, for any type of oscillation, the graph looks like a trig function. So it's not just going to be like a jagged bunch of V's. It's going to be more of a curvy, looks kind of like a sine or a cosine graph. All right. And then for the acceleration, okay, remember Newton's second law? Net force equals mass times acceleration. That tells me that the net force right here is proportional to the acceleration. So whatever the net force is doing, that's what the acceleration is going to do. They're always going to have the same shape. So if this is what my net force graph looks like, then my acceleration graph is going to have the exact same shape because they are proportional. All right, now for position, it's as easy as it seems, right? We talked about position earlier. Anything above B is a positive position. So A is a positive position. B is a 0 position. And anything below B, so that's C, that's a negative position. So we go through and mark our different stuff. So when it's at A, that's above B, that's a positive position. At B, it's a 0 position. At C, it's a negative position. And then we just follow that same pattern. Okay? And just like before, when we are talking about velocity, remember when something is stretched out as far as it's going to go, it has the most elastic energy, right? And when it's here, when it's at points A and C, it's changing direction. So its velocity is 0. Right? So if its velocity is 0 at A and C, it's going to be moving fastest through point B. Right? It's had that force pushing on it the whole time. It's been accelerating this entire time. And then now it's going to start slowing down once it passes. So at B, it's always going to have a maximum velocity for whatever direction it's moving, up or down. So when it's at A, we have 0 velocity. Let me make a, right? Because we said at A and C it's changing directions, right? So it has a 0 velocity at A and C. So at A, it's at 0 velocity. If we're going from A to B, the thing is going down, right? A is up top, it's going down to B. So it's going down to a negative velocity. At C, that's an endpoint, so it has 0 velocity. And then from C to B, it's going up. So it's moving in the positive direction. So at B, it's going to have a big positive velocity when it's moving from C to B. And then we follow that pattern all the way through. All right. And kind of like we talked about last time, when you think about the motion graphs we have, you have position graph here, right? Velocity here, and then acceleration. So position, velocity, acceleration. Either we kind of memorize the shapes of these, or if we have a little bit of calculus, in our toolbox, we talked about this in the last video, but this position graph, right? This graph looks like a cosine graph, right? And so if you want to go from a position to a velocity function, you can always take the derivative. And so the derivative of a cosine is a negative sine. And so that's what we have here. So we go position, derivative of position is velocity, and then the derivative of the velocity is acceleration. So you go cosine, negative sine, negative cosine. And now you're seeing why you learn that stuff. All this stuff actually happens in nature, which is cool. All right. So if you guys have any questions, make sure you text or email me or anything like that, and I'll talk to you guys later.